Let's talk a little bit about categorical data. To have a solid understanding of what categorical data is, let's have a look into a first uh, brief example here. So let's look over to my computer screen here, and what I have here is simply a picture that describes a group of people. So think about a lot of time that when you are filing out a job application or filing out a school admission. So somewhere in your application, there has to be a line asking for your gender. And so let me quickly bring up example one right here for you to recognize what category data is. But so gender is one kind of data where you can look right here into the picture. So this group of people, any group of people, we always have two different kind of gender. So the gender here can be either male or female. And so just like that, in my picture of the group of people here, and you can see that just by the look right here, so we got a few males people here in this picture, and we got a few females here in this picture. So these are the female, that's a female, that's a female. So we got a few females, we got a few male here. So what I see here, so for the people who are collecting the information about gender from a job application, then they are looking, so the way how people are looking for that kind of data, they see gender as a categorical data. So gender here is the categorical data. So what about being male and female? So being male and female are the different values. We refer to these as values of the data gender. And that's how we understand about categorical data. But so what exactly and why do we call that categorical data? Simply because each value here, being a male, is a category. And besides being a male among the gender, being a female is a different category. And that is the reason, that is why we refer to this bigger class of data here. So gender being the data, having two different values. And so we regard to gender as generally categorical data. And it has two different values. So each value of a categorical data is being a category. So here in this a quick little example over here, gender being the categorical data, then each category here, male and female, being a category. And then to continue, of course, we are still currently being in example one. And so we already understood that gender is our categorical data, and these are two different values being the two different categories in this data. But so now we've talked about this a little while ago. But so one big characteristic of a categorical data is that the value has no ordering. And what I mean is, if we take a male value and comparing that with a female value, we cannot really say that male is greater than female, neither the other way. We cannot say female is less than male. So ordering here do not exist. Any kind of ordering doesn't exist. We just simply cannot put data in any particular order at all, because it just basically means nothing. We cannot say male is greater than female in which way. Is that a body size, or is that a height, or is that weight, or is that anything else? There are a lot of factors. So basically, for being categorical data, we simply treat that in the most simplest way. There are two different categories. So they do not have ordering data. They just simply do not have that ordering exist between them. So same way, we cannot say female is less than male, or we cannot say male is less than female in any way, because in which way do we see that? Another characteristic of categorical data is that, let's say we take a value and we subtract another value in the data. We take a value and we add another value in the data. We take a value and we multiply with a different value in the data, or we take a value and divide by another value in the data. When we're attempting to do these, well, in daily term, we call this, any of this work right here is we're doing mathematical operations. So these are all the common mathematical operations. And so when we're attempting to do these in a categorical data, the first thing we ask ourselves is, does any of these give us a meaningful outcome? So what is the meaning of male minus female? It makes no sense. It makes no meaning for us. What's the meaning of adding a male with a female value in the gender data? And obviously it has no meaning. It has no useful application. And in the end, it's makes no sense. And so now you can see that other characteristics in a categorical data is that any mathematical operations do not exist. So all mathematical operations do not exist for the categorical data. And so as a bottom line, before we move on a little any further in terms of categorical data, let's summarize what we have seen so far throughout our first example. But so for categorical data, the first thing to keep in mind is any kind of ordering does not exist. So ordering, or for short, I'll just simply say there are no ordering of the values. We can't put the values in order. So that's the characteristic number one right here. Very opposite with numerical data we've been spending a lot of time on. Numerical data had all that the ordering. We can put data in order so that we can find mode and we can find mean and we can find medians and all that. But for categorical data, we just don't have any ordering. There are no ordering of the values in categorical data. There are no mathematical operations, so no math ops between any two value. In categorical data. And sometimes you might recognize I use the term cat data, which represent categorical data. And so if working with categorical data does not allow us to put data in order, does not allow us to do any mathematical operations, then the big question now is, what can we do with categorical data? So let me bring up example 2 over here. And in this example 2, we're going to walk through a couple of different data. And we're going to recognize what we can do. And keep in mind, we're completely ignoring all that ordering, basically all that numerical sense about the data here. So every category is one category on its own right here. And so now, let me bring you into example 2. So how about example 2? Let's still look at the data where I look at the people right, the picture of the group of people right in front of us here in the screen. So this time, and I'm going to call that part A. How about, so for part A, I'm going to consider gender. So in this particular picture, so gender in the picture, because any group of people, the group of a group of students in my class, a group of students in the auditorium, a group of football players, we have a group of people in anywhere. But here, let's look at the gender in the picture, because my picture here has a group of people. So of course, gender has only two values ever, male and female. And I have to clarify that when we're saying that male and female, we're talking about the naturally born gender that comes with the person. So of course, we don't consider any kind of the artificial gender at all, because understandable that in these days we're living in the 21st century, where the technology has grown much beyond our imagination. But in the end, statistically, I'm looking only at the naturally born gender right here. So in a group of people like this, the first thing we can do, again, remind yourself, the N count is famously known for how many values totally there. So including all males and females, we are looking at, so after a quick count, I found there are 13 values being in the data. I mean 13 people, and those 13 people is going to carry any of these values right here. And so now in that group of 13 people, so my n count how big the data is, 13 of them. I'm gonna quickly I'm gonna be able to make a count here, but male and female, simply 2 columns. And now let's look for the count. So the count here says in my group of 13 people, I found 7 of them. So, and here I'm talking about the actual count here. 7 of them are the male value there. And the other, of course, 6 people are carrying the female value in that group of people. So this count right here, so right now I keep using that term count, but the count here is formally regarded as the frequency again. So this frequency in this data, having 13 data values, then we're looking at the frequency of being a male is 7, and the frequency how often we see a female in this data, 6. And so in the world of categorical data, we can actually be a little more creative than just simply getting the actual count. So frequency is the actual count out of the whole group right here. But so once again, taking advantage of that total we already had previously, n equals 13 right here, then I can creatively put 7, the actual count, or the actual frequency of the male category right here, or of the male value, I'm going to divide as a fraction by 13. And this fraction in percentage, as a percentage, it gives me 53.85%. Let me rewrite my work here. 53.85%. And then so on the other hand, similarly, with my female counter here, the actual frequency is being 6, and I'm going to creatively, and I use that term creatively, just think about when we are those first generation statisticians. So we've looked at in every different ways how we can creatively use the understanding we have here. So 6 out of 13 gives me a 46.15% in percentage. And so what I did here creatively is that I put my actual count, my real frequency, out of the entire total, out of the n number, and I came up with a what's so-called, so this row down here, I'm indicating any of these is being regarded as the relative frequency. Okay, and so the idea of having a relative frequency is quite simple. All you do is we get the actual count and we put that over the total in your data, the total number of values in the data. Same way right here, we're looking at the relative frequency for being a female in this picture over here. It's simply going to be 6 out of 13, or as a percentage, it's 46.15%. And in this example, let me introduce a different data. So let's look back into my computer screen again. This time on my computer screen it shows a picture of various objects with colors and different kinds of objects right here. And it seems a little kiddo here, but actually do not look down on that. It has a lot of categories that we can recognize through right here. Okay, so right here among the objects, and we're still in example 2, but let me just bring up a different type of data here, but it's another categorical data. But how about, and one more time, let's have a look at our objects here, our different shapes here. And so here the data I'm looking at here, let me underline that, but let's look for the color of the shapes, or the different colors of the shapes. And so right there in that picture over here, then the colors can be now regarded as the categorical data we're looking at, and the different values. So I haven't done this earlier in a past example, but now let's track it down over here. But since we recognize color as being the, or simply color, as generally regarding to any color of the shape here, then here we're looking at different values, being we have some shapes being blue or dark blue. We have some shapes being red, some shape being green, and some shape being yellow. So unlike the male and female, unlike the gender, the categorical data, this categorical data right here, and in our current data that we're having, then we have 4 different values right here, and each of these exists as a category again. So we got categorical data here, each value is being a category. And so now, and like I said, we can't really say that blue is greater than red, or red is less than green, or whatever. None of those properties of numerical data exist here. We cannot order the values. So you can put red, blue, green, yellow in whichever order you would like to, but that's not the point. What we can do with this categorical data here, we're going to once again be able to give the count. So I'm going to have to make a bigger table here. So 1 column for the blues, 1 column for the red, 1 column for the green, and 1 column for the yellow. All right. And so let's start out with finding the actual count, the actual frequency here. So as far as the actual frequency, and allow me to use a shorthand writing right here. But the actual frequency, the actual count for the blue right here, there are 4 blues. And I'm not talking about which shapes they are. I'm only looking for the color being blue. So I recognize there are 4 shapes having the color blue in my picture. And then there are 4 reds. There are also 4 greens colors, and there are 4 yellow. So, and then once we've had the actual count here, the actual frequency, now let's quickly pause the video and look at the picture here. But our end count in this data, we are having a total of 16 shapes, 16 objects. And so in that way, I'm ready to make my way into the relative frequency. So the relative frequency for blue is being 4 out of 16, or it makes in percentages, as a percentage, 25%. For my red category, for those of the objects falling into the category being red, I'm looking at 4 out of 16. And as a percentage, it's 25% of the data. So what it says here is relative to the entire data, and that's why it's called relative frequency, relative to the entire data. Blue takes 25% of the data. Relatively, red takes, those red shapes takes another 25% of the data. Those green shapes right there take 4 out of 16, which is also another 25% of the data. And here we're looking at 4 out of 16 again, being another 25% for the yellow object. And that's how we find relative frequency as well as the actual frequency. But of course, we always need to start out with the actual frequency first. Anytime working with categorical data, we can also come up with graphs to represent the categorical data, even though the data does not have the numerical sense, but we can also come up with graphs. And so the first type of graph I would like to introduce here is the bar graph. And so to quickly understand how to construct a bar graph out of a categorical data, let me just quickly put up that example about, so let's look back to that example 2a, that example 2a that we had about, it was about the data was gender in the picture. And so gender, of course, I was only regarding the two naturally born biological gender, male or female, the only two values. And once again, let's have a look into our screen right on the computer screen right here, our picture on the computer screen. And so remind yourself that we've learned in example 2 part A that we've had the n count as being 13. And we did construct it, and here it's not a bad idea to redraw that table, but we had that so the male count as a category and the female as another category. So frequency, the actual frequency for the male count was we came up with there are 7 males and there are 6 females out of in the whole total n equals 13. And so immediately looking at the actual frequency of your categorical data, then now we can construct a what's so-called a bar graph. And really the bar graph, but it's really just the basic bar graph. Okay, and so with an empty space now, this is how the bar graph for that gender in the picture looks like. So we're still going to need to have a horizontal axis and a vertical axis, but really the horizontal axis here is only simply a place to put down the categories. So I'm going to pick a space here, and I'll call that the male category, and I'll pick a different space. I call that the female category. And then the male category comes up to as high as being, let's say, I'll go with 14 being the maximum scale, so 7 is exactly halfway. So my male count was 7. So I'm going to rise my category as a column, as a rectangular column, as a bar, and being 7 in the count right here. So halfway at 14, and scaling how far that is just pretty much depending on your choice right there. So 7 is the count for male, so it's being represented as how high that rectangular column, that rectangular bar is. And so female is being another bar and being only 6, so slightly below. Okay, 6 is about there. Okay, so slightly below. And we have another column. We have another rectangular bar here, slightly lower than the male one. Okay, so female is this column. And that's how we have a basic bar graph. So it is a bar graph, but it's also known as the basic bar graph because it just reflects, or it represents straight out of the box, the basic frequency of these. So of course the frequency being arranged on the vertical axis, and really we don't have any numerical meaning on the horizontal axis here, so don't even put an x value or whatsoever. So I've seen common mistakes like this regarding this basic bar graph right here, that first of all, people trying to put a line that connects to the tips, because in the end a bar graph does look like a histogram a little bit. I mean, it does have the bars, the vertical bars rising up and down right here, somehow some bars high, some bars low. And so mistakenly I've seen my students and a few other people connecting the tip of the bars right here with a line, and hopefully to look for a shape of the distribution. But now that idea, connecting the tips of the bars, was a good idea when it was in a histogram for numerical data, but here for basic bar graph, simply to represent the categorical data. Now doing this is actually not good at all, because Now, putting male here on the left column and putting female to the right column is simply just a choice right here. And who knows, tomorrow if I give the exact same lecture out of my own creativity, I can just recreate. I can just, the exact same situation here, but I can just simply change my mind and put, and I could have done this right in the beginning. That I could have just put the female in the front and to the left being 6, and the male bar comes a little later. I made my 6 a little too high, and so and my male bar is here being 7. And so remember what we've learned regarding categorical data is that they have no ordering. So you put male first in your horizontal axis here, then female, or we put female first, then female. It makes no difference. It's just simply to compare between the two categories, which one looks higher, which one seems to have higher count. That's all the basic bar graph serves as a purpose. And so once again, if we are attempting to recognize the tip of connecting the tips of the bars here to recognize the distribution shape, that idea is going to fail because it's not going to work here, because it's not intended. That's not what the bar graph is intended for. And then, no, if we were looking back at the histograms, that any histogram we've learned how to construct it, then the space between bars, back in the days of histogram, strictly no space. But here for bar graph to represent different categories, having space are actually quite okay. And as a matter of fact, it is recommended to have some space, a little bit of space between bars, between each categories. It helps the reader to read that a little better. Okay, so okay to have space between the bars. Okay. And then back to our data, recall from example 2a previously that we have already found, and even if you missed that video to find out what example 2a was all about, really this is all that comprehensive summary of all that example 2a is here. So the next step we did back in example 2a was to get the relative frequency. So 7 out of 13 was put into relative frequency or percentages. 7 out of 13 was 53.85%, and we remember we call that percentage the relative frequency. Relative frequency, or just relative frequency. Okay, and then for the other bar, simply put the actual count, the real frequency, over the total n count, and that gave us back in example 2a right there was 46 out of 46.15%. So these are the relative frequencies for this data right here. And so we can also come up with what's so-called the relative frequency bar graph right here. The idea is relative frequencies can also be placed on a bar graph as well. But so now, as the name is making that suggestion, you can see ahead or understand ahead of time before I put up the graph that it's going to be a bar graph. It's going to have column high and low, but it's the columns here is going to be intended to represent the relative frequency instead of the actual frequency as we have seen previously. So there it is. There's a vertical axis for the frequency, and there's a horizontal axis. I'm going to pick a space here. My creativity pushed me to put M on the left-hand side, but you can make your choice putting female on the left-hand side column. I want to pick another space for my female bar right here. And so the only strict requirements when you are doing relative frequency is that maximum full scale always need to be 100%. So set your own scale, but that maximum scale must be strictly 100%. And so in that way, it's easy to recognize that halfway is 50%. All right, and then quarters are the 25 and the 75%. So it's making it, recognizing those quarters and halfway is making it easy for us to draw the graph a little more successfully. It's not really the main aim out there in these modern day anymore that we have to build these things by hand, and we have tons of software out there in the market to assist you doing this, but I'll let that for you to learn that on your own. And besides, different companies, when they hire you to do these kind of work, they're going to have different training on your different software usage right there. So the male category is as high as 53.85%. So 50% is here. So all we, and like I said again, we don't need to really be exactly on scale right there, but it makes sense to be a little bit above 50. And it's actually it's 53.85, so it's about right there. And that's the reason why having a numerical label on top is always a wonderful idea, and it's a good idea. And I said 85, but I wrote 84. Okay, and so make a shade to assist your reader. And that's my male column. And then my female column also has some height, but this time the height is only, the female is only 46. It's taking only 46.15% in my data. So 46 is slightly below in a far scale, in a zoomed out scale. And of course, it makes sense that it's, all right. So I'm drawing my 46 is about that high. Okay, so. And that's why in the end, once again, it's always a highly recommended habit to put the numerical label of your frequency so that everybody can see it clearly and with number explained. All right, so that's what we have here as being a relative frequency bar graph. So what's good about this relative frequency bar graph? Why aren't we just simply be happy with just the basic bar graph? But here we have to actually go all the way to tearing it down to a relative frequency bar graph. No, it's all about assisting your understanding. The whole point of putting up a graph is to assist the understanding of, assist the viewer, the readers to understand, to have a good view of the data right here, to have a good understanding. So basic bar graph can only tell as a comparison between the two categories, who's higher and who's lower. So let me put up that scenario over here. So 7 is about here and 6 is about there. Okay, and so my male bar here is my female bar. So it simply tells me, looking straight and looking simply at the basic bar graph right here, then it basic frequency bar graph, then this is only telling me that, hey, among the two categories right here, then male count is slightly above, is slightly higher than my female count. But that's about all we can understand. But here, when you're looking at a relative frequency bar graphs, it still shows, it's still represented, and it still shows, it still displays that the male bar is higher than the female bar, so comparison can be seen. But another intention of the relative frequency bar graph is that, and you can see that we call it relative because it's intending the kind of data, putting your frequency this way is intending so that we can compare among them and also compare them versus the whole setting. So imagine I talked about set full scale right here being 100%. And so the relative frequency bar graph here compares among the columns and also compare how each column is being compared to the entire data. So your entire group of people is this big, this high, and compared to the whole group, then this male bar is about slightly more than halfway through the whole group. And then another intention, you can see I'm not skilled enough to do that, but think about if we can take this bar right here and stack it on top of that other bar right there, then the two height is going to add up and be exactly 100%, because it's the whole point of being relative frequency, the whole point of being percentages. All the percentages add up to be 100%. And so, as a matter of fact, there are quite a few times out there relative frequency bar graphs is being written in that way. We have a 100% here, and then there's one bar only. But among the bars here, then about a 50. 50% is exactly halfway, and so slightly up there is the male bar, and the rest here in a different shading right here. So this part right here is the female bar, and this part down here is the male bar. And you have quite a few different ways to be creative about this, but that is another just perfectly fine relative frequency bar graph as well. And then when you are working with relative frequencies, then there is a different kind of graph here that can be useful, but it's called the pie chart. Quite a few names out there actually. Some textbooks refer to this as a circle graph. And it should be the same thing. But the idea of being a pie chart or a circle graph here is that you got a circle, you got a pie. And so that pie is intended to represent one nice whole 100%. So your whole pie, your whole pizza here is 100% of the entire pie right here. And so for your relative frequency, when we are representing this gender in a picture, then remind yourself that we had the male count as being a 53.85%. So slightly more than halfway. And so in that way, here's my pie. Halfway is about here. Slice through that pizza right there. Slice through that nice circle. It's a halfway. But then we're going to need to be a little bigger than 50%. So about this big right there is just perfectly good enough. Okay. And like I said, we're not really going to need to be that far in exact precision. But so now that big bar over here represents 53.85%. And the other area that remains on this pie chart of mine is going to be the other relative frequency, which was 43 and actually I meant 46.15%. And of course, I should have been also color shading this. All right. So that is the way the way to use a different type of a graph, a chart, to represent your categorical data. And here the pie chart strictly is only for relative frequency. So female count here was 46.15. And so now that we've been talking about how categorical data doesn't have ordering, doesn't have mathematical operations existing among the data values, but even if we have a numerical data, let me bring up this example 3 right here. Even if we have a numerical data such as data 1 that we've been working with throughout the other lectures right there. So let's look at data 1 right here. And I'm going to once again turn over to the data that I have on my screen right here, my computer screen. So let's have a look at data 1 right here. And you can always pause the video to take note of the data 1 in case you never had it. But so this time for data 1, admittedly data 1 was, so I just got to make a note here, data 1 was a numerical data. We worked with them, we were able to add the values there, we were able to arrange the values in order, and that's the whole point, the whole reason why we have data 1 being given in 2 different versions here. Then there's data 1, the unsorted, the unorganized version, and there's data 1 being the sorted, the organized version. So data 1 was thought to be numerical data, and it was. But here's the thing. I am going to construct a table where I'm going to say, so how about being the data value? Okay, so being the data value, I'm going to see that, hey, in my data 1, and pretend that think about if we pretending that we have never, this is the first time ever we look at data 1, or for me pretending that, you know, if we have to try to remember what was in data 1, then maybe right on top of your head, we can't remember who came first in the data then, but I can remember vaguely there's a 76. And so let it be right here. And then there, I remember, oops, there's now the 60. And then things start popping back out right here. And so I remember now there are 88. So now what I'm demonstrating here has the entire intention here that what if we only regard to these, what we so-called numbers, but now we completely look at them only as objects. So think about, hey, in my data 1, there's some object being 76. There's some other objects that comes with the two numbers 6 and 0. There's some other objects being labeled with 88. So now if we're regarding these values being objects, being different categories right here, then we have a few 76 here. So back in the data, we have a few 76. So I spot another one here and I spot another one there. The point I'm doing now is that we are purposely we intentionally ignoring all the numerical meanings of these data values, but we only regarding to these data values as different objects, as different categories. So every one of them is equal to, in a sense of just being a category. And so 76 has its right to come first. It's just something that came out from my memory. And so 76 here in the data, we've got, if we can count through, there were 6 of them. And so this 6 at the bottom row over here I'm writing, that's the frequency again. So now what I want to show everybody in this example here is that we can purposely treat a data that was once a numerical data, but we can now purposely treat this data completely and entirely as a categorical data. So 76 of mine right here, once we ignore all that mathematical, all that ordering, all that numerical nature of that 76, then it simply just remain as a category. So it has frequency 6, 60 has frequency 3, 88 has frequency 5, and that's all I can remember. And of course we can always look back at the data and count through. And then I remember there were 80, and the count for that, the frequency for that was 6. And then there were the 72, and there were 8 of those. And there was 64, 4 of those. There were 68, there were 5 of those. And then of course there's more into the list right there, but I'm unfortunately running out of space. But so, after understanding my intention that we are moving in that direction where we're still looking at data 1, but we're completely ignoring all that numerical data, and now we're treating any of these as an object, as a category, then these are just simply to count how many times we see an object being in that 76 category. How many times, there are 3 times we see an object being in the 60 category. And so, once we got the actual frequency, we can once again construct the relative frequency. So the relative frequency. So here, remember the famous n count for data 1 was 40, just to remind everybody. And maybe I should have put that in a different corner of my paper. So n count for this data 1 was 40. And so to get that relative frequency, 6 out of 40 is my relative frequency for 76. And so what we're looking at here is being %. 3 out of 40 is the relative frequency for 60, and that's in percentage. That's 7.5%. And then 5 out of 40 as the relative frequency for 88, and that gives me in percentage 12.5%. 12.5%. And then here we have the same frequency count right here, 6 out of 40. So as a percentage, it equals to 15%. 72, there are 8 of them. 8 out of 40, which is the same as a 20% here. And then so on and so on. 4 out of 40 is the same as being 10% of the data. And then, and here 5 out of 40, and that's being here 12.5%. And of course, here I'm running out of space, but anyone who viewed this video, if you have time, I highly encourage you that you finish out, because I still remember we have some other values that's left behind right there, and now we're treating those other values as categorical. So if I remember correctly, there was a 96, there was a 104, okay, and there was also a 124 right there, and there was only one of that and one of that, which makes it this is 1 out of 40, and that was 2.5%, and this is also a 1 out of 40, which is the same relative frequency, 2.5%. All right, and this is my final table representing the data 1 as a categorical data, where it lists the frequencies in this row right below all the recognized values, being, so categories we have up here, corresponding frequencies are here, and these are the relative frequencies, and that is how we can purposely see a numerical data, even though a numerical data, but we can purposely see that as the categorical data. And so apparently it looks like there isn't too much to be done with categorical data. So why do we even study it? So I have to clarify it. There is not too much, but really there is not too much to be done mathematically. So yes, I agree that on categorical data, not much to be done, but mathematically. We can't add, we can't subtract, we can't divide, we can't multiply, we cannot do any of those, and we cannot even put them data in order, the values of categorical data in order. However, they live in any of our examples. So the reason we're doing the categorical data, or at least have to have a brief look into the understanding of categorical data, because if we now have a look at any of the example we have done in the past, just are the probability problems, and the most the recent one we've learned was this one here, where we had a probability of from a contingency table like this. So we're not going to go back and learn probability, but the whole time back then, any time that we were doing find the probability of a business student, of a math major, of an engineer, so any of these is a category. So being business, once again, I repeat, is a category. Being a math major is a different category. Being an engineer major is a different category. And we also have a different kind of categories here, being different types of categorical data being arranged in this table. Being a freshman, a class rank is a category. Being a sophomore is a different category. And being a junior is a different category. So categorical data gives rise to what we used to call events in a probability problem. And so for now, I can just quickly, I can just briefly mention how categorical data already had part of it in our study previously. And throughout the rest of the quarter, any other lecture later on, if we keep having a close look into the existence of categorical data, it lives in any of our examples, and it lives in any of our lecture throughout the quarters later on.